So today we're happy to have Pablo Alvarez from the IAS, and he will tell us about the K-ring of Steinberg variety.
Okay, thank you, Mackie. So yeah, this is the first talk in a series of talks that's going to conclude with proving some of the theorems in the paper by Roman Beshukovnikov, two realizations of the affine Hecke algebra. And today what I'm going to discuss is the decategorified results of that paper. So in that paper, there's an equivalence between a derived category of coherent sheaves on the Steinberg and some category of perverse sheaves on the affine flat variety, some monoidal equivalence. And the result that I'll talk today about is a classical result by Kashtan, Lustig, and Ginsberg, which basically is the decategorified result. So that is an isomorphism of the K-ring of the Steinberg variety with the affine Hecke algebra. And I'll explain all these components, in particular a bit of the geometry of this Steinberg variety. Right, so let me jump in. So, right, let me begin with some notation. So G is going to be a semi-simple, simply connected group. The simply connected is basically makes life a lot easier. B is going to be a Borel, and T a maximal torus. And then I also have notation for the Lie algebra, for the Weil group, and a set of simple reflections, and for the character lattice. Now, given all this information, I can construct the Grothendieck-Spring resolution. So what is this? So this is the variety of pairs, X and B, where X is an element of the Lie algebra, and B is a Borel subalgebra, which can be thought of as a point in the flag variety, satisfying the incidence relation that X is, in fact, an element in that Borel subalgebra. Now this has an action of G by conjugating both the Lie algebra factor and acting on the flag variety, and it also has an action of C star, which acts by scaling the Lie algebra and does nothing on the flag variety factor. And with this, we can construct the Steinberg variety. So this is the variety that's going to be of interest in today's talk, which is the pullback of this, the product of this Grothendieck-Springer resolution by itself over the Lie algebra under the obvious projection to the Lie algebra of this variety. But as so with this, we can already consider the K group of this Steinberg variety, the G times C star equivariant K group of this Steinberg variety. But as I say in the title, this should be a ring. So what is the ring structure on this K group? Well, this is a ring structure that can be put really on all of these pullbacks like this, which is defined as follows. So we can consider the triple product of this Grothendieck-Springer resolution, and then the convolution of two K classes, F and G, works as follows. So I'm going to pull back the first K class along the projection to the first two factors. I'm going to pull back the second K class along the projection to the last two factors. I'm going to tensor them in the triple product, and I'm going to push forward along the map from the first factor, that maps to the first factor and the last factor. And this operation here is going to give us some ring structure on this K group. And this is the ring that we're going to consider and that we're going to prove is isomorphic to the affine Hecke algebra. So I guess that begs the question, what is the affine Hecke algebra? So the affine Hecke algebra is, that I'll denote by H, is an algebra over Laurent polynomials generated by the following generators. So it has generators TS for S simple reflections in the Weil group W, and E lambda for lambda in the character lattice. And these generators are subject to the following relations. So the first is that these lambda, this character lattice, well, that there's a group algebra of the character lattice inside this algebra. So these multiply just in the obvious way, and E0 is just the identity, just the one. Then the TS's satisfy the typical quadratic relation of some Hecke algebra, such as this R2. And then there's some commutation relations between the E lambda and the TS. Namely, there's two cases that are enough to consider. The first is when lambda and the simple root pair to 0, then TS and E lambda are just going to commute with each other. And then there's the case with lambda and alpha pair to 1. And then we're going to have this relation here, R4. And then, of course, R5, the last relation, is the braid relations between the TS, like between different TS for different simple reflections, which I won't write down. But with these relations, this algebra is free over Laurent polynomials, and it has a basis given by E lambda TW, where this TW for some reduced expression S1 through Sk is just the product of the generators T S1 Sk, which doesn't depend on the reduced expression by the braid relations.
Pablo, excuse me.
Yes.
Lambda is a weight lattice, right? Not the co-weight lattice.
Right. Yes.
So you rather pair with corals.
Sure. That's fine. Better. Yes. Okay. Then that needs to be correct throughout, I guess. Okay. Yes. Right. So. Right, so this defines the algebra, and now I want to state the result and give a bit of an overview of the idea of the proof. So this K-theory of the Steinberg variety is an algebra over just the K-theory of C star of a point, which is isomorphic to this Laurent polynomials. And as algebras over this, we have an isomorphism as stated in this theorem. And what's the idea of the proof of this isomorphism? So what we're going to do is we're going to introduce some modules for the Hecke algebra and a module for the K-theory. We're going to give an isomorphism of these two modules, well, a priori just as vector spaces, in such a way that the generators, which on H are sent to the obvious generators, and on the K-theory are sent to particular classes that we will see later, commute, like that this diagram commutes under this identification that we give. And once we have this commutativity of this diagram, we're going to check that this map that I denote I is injective, or in other words, that the module of the K-theory of the Steinberg, this module of the K-theory of the Steinberg is actually faithful. And so any relations that are satisfied by these generators here on the action of the on the module are already satisfied on the K-theory itself. And because all the relations defining the algebra H are satisfied here by this commutativity, they are satisfied here if we can prove that this is indeed injective. And so this induces a map F, once we know the injectivity of I, a map of algebras F. And to prove that this map F is an isomorphism, what we're going to do is we're going to introduce a filtration on H and a filtration on the K-theory, such that F is a filtered map and such that the graded graded map is an isomorphism. And then F was already an isomorphism to begin with. Okay, so any questions about the idea of the proof? Okay. So before going a bit into the geometry of the Steinberg, I'm gonna give a few general facts of K-theory that might not be familiar, and see how they're going to play a role in this in this talk. So the first result is the cellular fibration lemma, which states the following. So if we have some f, a filtered space over some space x, so f is filtered by some subvarieties with a g action. So f and g have a compatible g action, and all these filtered subspaces also have all these filtered subvarieties also have some RG stable, in such a way that the difference between one of the filtered pieces and the next one is actually an affine space fibration over the base x. Then we have the following result, namely that the K-theory of this space F is filtered by the K-theory of all these subvarieties, and that the associated graded, that the subquotients of this filtration are given by the K-theory of these differences. And because these differences are just affine space bundles, the K-theory of them is just the same as the K-theory of the base. Or in other words, under these conditions, this allows us to give F as some sort of extension of the K-theory of the base X a bunch of times. Right, and we will use this filtration, a filtration induced by exactly such a setting, to introduce the filtration that I mentioned here in the third point, to introduce the filtration on the K-theory. Yes, throughout this talk, K is K0. Yes, so this is basically some statement that the map, the long exact sequence of K-theory, the map from K1 to K0 is 0. That's the basic argument of this statement 1. And then statement 2, that of K-theory is localization theorem. So under the setting of the first theorem, assuming that one of the factors of this group that acts is a torus, and if we denote by RT the representation ring, then we can look at this K group of F at the generic point of RT, and do a similar thing for the fixed points of the torus. And we're going to get an isomorphism provided that the same result holds for the base variety X. And in the setting where we're going to use it, the torus is going to act trivially on our base variety X. So this statement for the base variety X is just going to be obvious. And so we're going to get this result holding for F, which is going to be this Steinberg variety. And this localization theorem here is going to basically play a role on the injectivity. So these two theorems play a role respectively on the surjectivity and, the isomorphism and the injectivity of this map I. Okay. Right. So with this, let me give some basic facts about what the geometry of this space of this Steinberg variety looks like. So this Steinberg variety, which is just the product of two Grothendieck Springer resolutions over the Lie algebra, lives over a product of two flag varieties. And this product of two flag varieties, we have a nice filtration of the space, namely by G orbits. The G orbits on pairs of flags are in bijection with the Weil group. And we're going to denote by YW the orbit corresponding to an element W. Okay. And what we're going to do to understand this Steinberg is we're going to look at what it looks like over these orbits YW. Now, over an orbit YW, I claim that the Steinberg is just a vector bundle. Namely, the fibers are just given by, so if B is the Lie algebra of the Borel that we've chosen, we can take that, intersect it with the same conjugated by a W. So this is some vector space, and it's easy to see that the fiber of YW in the Steinberg is given exactly by this intersection, and so that this map here is a vector bundle. So this is, right, as I say, a vector bundle over this base YW, but even further, the closure of these ZWs give all the irreducible components of the Steinberg variety. I mean, they're clearly irreducible because they're vector bundles over something that's irreducible. But in fact, these are distinct irreducible components, and they're all the irreducible components of the Steinberg, and we'll see this a bit further in the next slide. Right, and this filtration of the space by these CWs is exactly going to be the filtration that's relevant to the cellular fibration lemma. So to see this, note that YW I can further map to G mod B by just projecting to one of the factors, let's say the first factor. Then the fibers of this map are just going to be the Schubert cell of W. So that is an affine space of some dimension. So this map here is just an affine space bundle. And so when we compose the projection from ZW to YW, which is a vector bundle, and from YW to G mod B, which is an affine space bundle, this gives us the composition, which is an affine space bundle over G mod B. And so these pieces, CW, satisfy exactly the condition of the cellular fibration theorem, where our base is going to be G mod B. So the K theory of the Steinberg is just built out of the K theory of G mod B a bunch of times. Well, W many times, I guess. Okay. And so now let's look at some easy components of this Steinberg variety and see what they look like. So the first, the component of 1. So the orbit of, the G orbit corresponding to 1 is just the diagonal, where the two flanks are the same. And so it's also easy to see that, in fact, the component, this Z1, is just the Grothendieck-Springer resolution diagonally embedded on in the Steinberg. So this Z1 component is very easy to understand. It's just the diagonal component of this Steinberg. Okay, and so what does this look for other components, or in some easy situations? So the first to understand this space a bit better is to consider the following map. So we have a map from the Grothendieck-Springer resolution to the universal Cartan. So this quotient of a Borel by its unipotent radical, they're all canonically isomorphic to each other and canonically isomorphic to universal Cartan. And so we can consider the map that sends a pair XB to just the element X, considered as an element of this universal Cartan. So this map also plays a role in understanding the global sections of this Grothendieck-Springer resolution, namely the global sections. They have no higher cohomology, and on H0 they are given by the structure sheaf of this variety under the map. The map to T is this, and the map to G is the projection to the Lie algebra. Okay, and so what I want to look at a bit is what this Steinberg variety looks over different points of T. So we have a map from the Steinberg to just one of this Grothendieck-Springer fibers and then projecting down to this T. And I want to see what this looks like over a regular semi-simple element and over 0. So over the regular semi-simple element, it's not very hard to check that this is actually just going to look like W copies of G mod T. So W copies of some irreducible thing. And in fact, these W copies, each one is in one component. So again, here we see the W components now as disconnected pieces. And another way to understand the components is just as the closure of what happens over the regular semi-simple locus, over these W disconnected pieces. Right, this is going to give us another way of seeing the components. And the other point that I want to look at is 0. So the fiber over 0 can also be understood as the Steinberg variety, but now instead of considering elements in the Borel, we would consider elements on the radical of the Borel, on the no-potent radical of the Borel. And what we would get in that case is just a union of conormals over these orbits, YW. Yeah, I'm not going to explain how you get this, but right, you can get this. So what does this look like in the particular example of SL2? Right, so if we look at this in this projection from the Steinberg to just the Lie algebra for SL2, and more precisely, we look at it over this fiber at 0, we're going to get just no potent elements. So the image is just going to be the no potent cone. And the two components are going to be, as I say, conormals to orbits. So what are the orbits? So the first orbit, the orbit corresponding to 1, is just the diagonal, as I said before. And the conormal to the diagonal is just the same as the cotangent to P1. And then there's the other orbit, the orbit corresponding to S, to the simple reflection. And this is just going to be everything but the diagonal. So it's some open thing on P1 times P1. And so the conormal to an open thing is just the 0 section. So the second component is just P1 times P1 with the 0 with the factor on the Lie algebra just being constantly 0. So these are the two components in the case of SL2, and the map to G looks as follows. So the cotangent of P1 just maps to the no potent cone as the Springer resolution in the usual familiar way. And this component Z1 is just completely crushed into the point 0. So that's what the example, the space looks like in SL2. And we're gonna, in the next few slides, we're gonna try to look a bit further into what happens in SL2 by looking at families of the picture in SL2 to understand these TSs, this generator's TS, and their relations, the relations between TS and E lambda. So maybe I think this is a good place to stop for the first time. So yeah, any questions?
What is your reference for equivariant K-theory?
The structure of the proof and the facts about the equivariant K-theory are just from Chris and Ginsberg. Yeah, the computations a bit later, they also appear in Chris and Ginsberg, but I think they're wrong there. And I've just decategorified a paper by Peshukavnikov and Risch, titled something like "Braid Group Actions on the on the derived category of the Springer resolution" or something like this. But the structure of the proof, and in particular all the facts of K-theory, are in Chris and Ginsberg.
We'll start back again in a few minutes, let's say 3:33 or so, but feel free to ask any more questions if there are any. If that's okay, I think we can start the second part.
Okay. Right. So in the second part, I'm gonna focus on the actual proof and the actual well, not the computations, but what the idea for the computations is. Right. And so the first part of the idea was that I needed to assign to the generators some K classes in the K-ring of the Steinberg variety. And the assignment is going to be as follows. So E lambda is going to be sent to the diagonal push forward of these line bundles O lambda, on which come from G mod B, just the line bundles on G mod B that give you line bundles on G total by pullback. And the generator TS is going to go to basically to the structure sheaf of these components ZS for S, the simple reflection. And there's going to be a minus so that all the relations work, but whatever. Basically the structure sheaf of this other component. To study most of the relations, I'm going to look at the following map. So I introduced this Grothendieck-Springer resolution as something living over G mod B, but I can introduce sort of partial Grothendieck-Springer resolutions living over partial flag varieties. And so, in particular, I can look at this over the partial flag variety corresponding to the minimal parabolic given by a simple reflection S. And it's defined in a similar way. So I can understand points of this partial flag variety as parabolics of this type, as parabolic subalgebras of this type. And then I take pairs of elements X in the Lie algebra and parabolic subalgebras, subject to the relation that X is in the corresponding parabolic subalgebra. The statement that I was saying of looking at what happens for SL2 is the statement that somehow this map looks like the Grothendieck-Springer resolution for SL2, but in families. You sort of this map here is just the map for SL2, but in families. And so what we're going to look at is sort of somehow this small kind of Steinberg variety looking kind of thing, this pullback here, which is the union of just, this lives in the Steinberg. Yeah, maybe I should say this. So this is some subvariety of the Steinberg, which is just given by the union of the component Z1 and the component ZS for the simple reflection S. And all the relations between a single TS and itself, or a single TS and the E lambda, occur in this subvariety, because all these objects here are supported on this subvariety. So what we're going to do is basically work with this subvariety to check most of the relations, except the braid group, the braid relations, which involve a bigger spaces. Okay, so so what I'm gonna look at is the following two exact sequences. So I'm just gonna look at the structure sheaf of this pullback over this partial Grothendieck-Springer resolution, and this space here is two components, two irreducible components. So I can map the structure sheaf to the structure sheaf of either of the irreducible components, the ZS irreducible component or the diagonal irreducible component. And the kernel of those maps is going to be something supported on the other component. So if we map to the CS, we're going to get something on the diagonal. And if we map to this, we're going to get something on the other component. Now, to compute exactly what you get on the other component it is an explicit computation that, as I say, because this sort of looks like the SL2 case in families, comes down to some computation on P1, some explicit computation on P1, but it's slightly long. Yeah, so for references, this is in Rish's paper preceding the joint paper with Beshukavnikov. But let me, so to check exactly what kernels you get here, but let me just say a bit about them, mainly about this second one, in the case of SL2. So note that in SL2, this row, which is the half sum of positive roots, in the case of SL2 is just -1. And this row minus alpha in the case of SL2 is also -1. So in the case of SL2, this is just -1, -1. And this variety here lives over P1 times P1. And this is everything that lives over the diagonal of P1 times P1. And the resolution of the diagonal in P1 times P1 exactly has an ideal given by this line bundle O of -1, -1. So maybe that's why, yeah, it makes sense that the thing that you get here in the case of SL2 is -1, -1. And in general, this is this minus rho minus alpha is what you get to to resolve the diagonal inside the diagonal union this ys in G mod B times G mod B. Okay, right. So these exact sequences are gonna help us compute with convolutions by the structure sheaf of the component ZS. But before we start that, let's understand convolutions with the generators that correspond to E lambda, to these diagonally embedded line bundles. So convolving with these diagonally embedded line bundles is just a really easy to understand. Namely, if you convolve on the left with this, it's just tensoring by the line bundle on the left G mod B factor. And if you convolve on the right, it's just convolving on it. It's just tensoring with the line bundle, but on the right factor of G mod B. So these are, and it follows immediately from this that if lambda is 0, this acts just by tensoring by the structure sheaf, so they don't do anything. And it also follows immediately that they, satisfy the lattice, the group algebra of the lattice relation. So basically, that just if you convolve by lambda and then mu is the same as convolving by lambda plus mu. Like this is follows immediately from this description. Okay. So now what we need to check is these relations with TS. And so in particular, since we're going to use these exact sequences, we need to understand what this thing does, right? Like from this discussion here, we understand what this diagonal thing does and what this diagonal thing does. But we need to understand what this structure sheaf of this pullback does. And let me just say that, this is true for pullbacks more generally, but in this particular case of the pullback, convolving with this structure sheaf is the same thing as push forward and pullback under the corresponding map from G twiddle to GS. So if you convolve on the left, just apply pull and push on the left factor, and if you convolve on the right, then apply it on the right factor. Yes. Okay. So again. Right. So in particular, we're want to know what this action of pull and push looks like in line bundles O lambda when lambda pairs with the co-root alpha s to be 0. And let me just say that in under this situation, O lambda actually comes from pullback, comes by pullback from this G twiddle S, basically because the line bundle O lambda on G mod B comes from pullback from the partial flag variety. And so computing pull and push of things like this, just by the projection formula, amounts to computing pull and push of the structure sheaf. And computing pull and push of the structure sheaf, because this is looks like just the SL2 in families, looks like computing global sections of SL2 of this G twiddle and SL2. And the global sections, as I said here, is just computed by this sheaf here, which in the case of SL2, this here is just a free rank 2 vector bundle over the structure sheaf of the Lie algebra. Right, this map from T to T mod W in the case of SL2 is just 2 to 1, well, generically 2 to 1. And so, right, so this gives us, right, that we get a vector bundle of rank 2, but with the condition that the GM action on the two summons is different. There's one where the GM action is just a trivial one, and there's one where the GM action is shifted by 1, because there's a non-trivial GM action on this factor of T. And so we get this 1 plus Q. So 1 corresponds to this trivial, where GM acts trivially, and Q corresponds to where you have to twist by the GM character. Right, so we get this formula of the pull push in the K theory under this assumption that alpha S pairs with 0. And now we're just going to use this result star together with the short exact sequence 1 to compute stuff. And yeah, so this requires a bit of computation, but it basically follows from this first exact sequence. And this computation, you know, in the case of the structure sheaf itself, that we get this equation for the image of TS for this structure sheaf O of ZS. Right, so this quadratic equation is satisfied, and similarly, maybe the easiest way of seeing this actually is because O lambda comes via pullback under this map, that we have this commutation relation in the case of right in the case of TS with E lambda under the condition that lambda and alpha S paired with 0, which, yeah, again, we use this short exact sequence of ZS together with the fact that these O lambda come via pullback from this G twiddle S. So this gives us that we have the relation of TS with itself and the relation of TS with E lambda under this condition. And the only relation of TS with E lambda that remains is in the case when they pair to 1. Again, when lambda pairs with a coroot to 1. And to this end, we're going to use this second equation, this equation 2. So this equation 2 here gives us some relation in our K theory, which, using the properties that we've already proven before, can be restated as this equation. So this equation right here is the relation R4, the relation between TS and lambda that pairs to 1, in the particular case of lambda equals to alpha minus rho. Right? Alpha minus rho is some character that pairs with alpha S to be 1. And this is exactly the equation R4. And so to check the relation R4 in general, the thing that I claim is that it's enough to know it for one particular case. And why is that true? Because for any other lambda and this alpha minus rho differ by something that satisfies that lambda paired with alpha S equals to 0. So now using this equation that we know for a general lambda, and this for this particular one, we can prove the equivalent equation like this, but for any lambda pairing with alpha s to 1. Or in other words, what I'm saying is that we have checked now all the relations that only involve TS, like 1 TS and E lambda. The only the only relation that remains to be checked is the braid relations. Okay, and maybe let me ask if there are any questions before continuing to this.
Pablo, can I ask an annoying question?
Sure.
Just for the sake of asking a question, basically. So going back to your 2 key exact sequences.
Mm-hmm.
So I really liked the explanation on P1 times P1, the resolution of the diagonal.
Mm-hmm.
But what's the kind of corresponding thing on the for 1?
For 1? Oh, for 1. Yes, I don't know if I have any more convincing explanation, except you just work out as I say, both of these things reduce to some computation on P1, and this is what what the computation on P1 looks like. I don't know if I have a better motivation as to why this is what you should expect as the kernel here.
Because it kind of looks like, you're looking at the resolution of the diagonal or resolution of the anti-diagonal. And I don't see why there should be a difference, but I guess there's some vector bundle over this situation that...
I mean, no, you definitely... I mean, I don't see why you expect them to be the same. Like, there's something definitely happening in the intersection, whether you map to or you map from, that's different. As I said, I don't know why I expect them to be like this and this, but
Okay.
Well, yeah, sorry. Okay, so yeah, maybe I should continue with the right, and ending this proof. So as I said in the idea, what we need is some modules where these 2 algebras act such that they're isomorphic and that we have a commutative diagram like that, where T here is the set of generators. So these are the modules that we're going to construct now. So H E minus is going to be, so E minus is going to be this element in the Hecke algebra. And it's going to satisfy that for simple reflections, E minus TS times E minus is just minus E minus. In fact, it's going to just, by the description of the basis of H, we can see that the basis of this this left ideal here is just given by E lambda times E minus, and so it's isomorphic to this RT of Q plus or minus 1. And similarly, the K theory of the Grothendieck-Springer resolution, well, because the Grothendieck-Springer resolution is just a vector bundle over G mod B, the K theory is the same as just the base. K0 is just the same as the base. And now, because G mod B is just a single orbit of the group G, the K theory is the same as the K theory of the stabilizer of a point, which is B times C star. And the unipotent radical here doesn't change the K group. So the K group here is just the K group of the torus times C star, which is just given by this. Where here, the basis is given by the line bundles O of lambda that we've seen before. And we can give an isomorphism just by sending E lambda E minus to this line bundle. And to check the commutation here, let me just say that it's very easy to check that E lambda and the diagonal under convolution act compatibly under this isomorphism, because, as I say, the action of E lambda, the multiplication of E lambda by of E lambdas with E mu's is just the group algebra of the lattice. So this is very easy to check that everything's working okay. And so the only thing that needs to be checked is that the actions of the TS's are compatible. But now we've checked all the commutation relations between TS and E lambda are satisfied. And because these E lambda generate the module, E minus is a generator of this module under the action of just the E lambda. To check that TS acts compatibly, it's enough to check that TS acts compatibly on E minus and the corresponding structure sheaf under this bijection. So the only thing that we need to check is that if we convolve the structure sheaf of ZS with the structure sheaf of the Grothendieck-Springer resolution, we're going to get minus the structure sheaf of the Grothendieck-Springer resolution. And this, again, I don't write the details, but this is immediately checked by this exact sequence again, and this equation star in the case when lambda and alpha s pair to 0. Okay, so we have a commutativity here, and the argument can continue, but let me just say, just a brief remark that these modules will also be appear in the future talks. There'll be a categorification of this action. So not only will there be some equivalence of monoidal categories where the Steinberg plays a role, but there will be an equivalence of modules where the coherent sheaf on this Grothendieck-Springer resolution is one of the modules. Okay. Right, and so once we had commutativity from the idea of the argument, we just need injectivity here, which would induce, would prove the braid relations and induce an action, and then the idea of introducing a filtration and that the associated gradient is an isomorphism. So for the injectivity, as I said, the idea is just the localization theorem. To do this, note that by the cellular fibration theorem, lemma, this Steinberg variety has a filtration by ZWs. And so this K-theory is flat over the K-theory of G mod B. And the K-theory of G mod B is just this, right? It's just as a vector space, it's just the direct sum of copies of the K-theory of G mod B by the cellular fibration lemma. And so it's flat over this algebra. But in particular, it's flat over just the Laurent polynomials. So we can look at what happens at the generic, because it's flat, injectivity can be just checked at the generic point of these Laurent polynomials. But at the generic point of these Laurent polynomials, by the localization theorem, everything just reduces to the fixed points of C star. Now, the fixed points of C star on the Steinberg, as I mentioned before, is just G mod B times G mod B. It's just the base, because the action is by stretching the fibers. The action is just by acting on the Lie algebra. So the fixed points are exactly this base G mod B times G mod B. And the K theory of this is just the product of the tensor product by the Küneth formula. And this acts injectively on just one copy under convolution, which follows by the fact that taking the pairing that is given by take two line bundles, multiply them together, and then take global section, that pairing is a perfect pairing, which I'm not going to check, but can be checked. And it follows from that fact that this here is injective, so that this is injective at the generic point. Hence, this map was injective to begin with, as we wanted. And just to finish the idea of the filtration, so this Hecke algebra has a filtration H less than or equal W by taking the subspace spanned by E lambda TW prime for W prime less than W in the Brouillard order. And the K theory of the Steinberg has a filtration induced by these ZWs, again, using the Bruhat order. And so we need to check that under these two filtrations, the map that we've just induced is in fact filtered. So the first point is that the E lambda, which by definition go to just something on the diagonal, hence go to something on Z1, right? Which we saw was just the diagonal component. So these E lambda, which obviously lie in H less than or equal to 1, go to the K theory less than or equal to 1. And similarly, the TSs live in H less than or equal to S, but by the cellular fibration lemma, the Steinberg less than or equal to S is just the union of Z1 and ZS, which we have seen is this product over this partial Grothendieck-Springer resolution. And so, right, by definition, the TSs go to something supported here. So we have that at least at this level, this is a filtered map. So E lambda goes to the correct thing and TS goes to the correct filtered piece. And now for the general element, TW is just gotten by convolving TS, like multiplying TSs with themselves. Or in the K theory, we have to convolve the structure sheaf of ZS alpha 1 to ZS alpha K for S alpha 1 to S alpha K, a reduced expression of W. And the fact that the support is in the union of everything less than or equal to W in the Bruhat order just comes from the fact that the image of this product here over these partial Grothendieck-Springer resolutions is exactly given by this. And to see this fact that the image is given by this is just basically, if you want, convolution on the flag variety. Or in other words, the fact that if lengths add, the relative positions of Borel's add, multiply, whatever. So this is exactly the same statement, and the fact that this is a reduced expression. Right, so then E lambda TW, which is in H less than or equal to lambda, goes to K less than or equal to, H less than or equal to W, goes to K less than or equal to W, and so the map is filtered. And now note that the associated gradient of these two spaces, in one case, it's just E lambda TW, so it's a free thing, free rank one thing over this algebra, and in the other case, it's just the K theory of Z mod of ZW, which is just the K theory of G mod B, as we've seen before, and the K theory of G mod B is just this thing itself. So at least, right, the two look exactly the same. So there's hope that this is a graded isomorphism. And yeah, I'm not going to go too much into detail, which is good because I don't have too much time. But to prove that this is, in fact, an isomorphism, a graded isomorphism, this follows from the fact that the convolution of the open parts of ZS1 to ZSK equals ZW if S1 times SK is a reduced expression of W, and that the intersections that you need to consider when computing the convolution of these spaces are transversal. And from these two facts, it follows that the convolution of the structure sheaves is exactly the structure sheaf times something that's invertible. And then this gives us the required graded isomorphism, and hence we prove the result. Okay, let me finish. It's a bit over time. Thank you. Any questions?
Yeah, I have a question.
Yes.
No, that's not a question, but just a comment. So you mentioned some Kunet formula for something.
Yeah.
And I think this quite subtle. It's not obvious at all. I think it is true, but it's a subtle statement.
Yes, I agree. Again, this is also proof in this Kuhneth formula, and the perfect pairing are proven in the same. They're the same part of the same lemma in Chris and Ginsberg, and yeah, I agree. This is subtle.
But it's also proved in my paper with Kardan.
Yeah.
But was the subtle was not trivial. Anyway, yeah.
More questions for Pablo?
It was a very nice lecture. Thank you.
Thank you.
So perhaps for the youngsters in the audience, there's Borel's description of the cohomology of like the B equivariant cohomology of G mod B is something like R tensored over invariance with R. And then that statement's the K theory version of that. So I guess if you write this out, it becomes kind of, you know, basically like the representation ring tensored over the invariance with the representation ring.
Oops, sorry. Oops. So it follows from this and Kuhneth, this description of the Borel, and I guess, yeah.
And Pablo, can you just go back to that bit, because I was a bit lost when you, so let's say that we know that statement, one more back, I think. Or, okay, keep going, sorry, to what you were calling the Kuhneth formula. There we go.
Oh, right, yeah.
So this is probably really stupid, but just so, so let's assume that we know this, why does it imply the injectivity?
So convolving like the convolution action of this product with G mod B is just given by basically pair this with this and then take cohomology. And I'm just saying that it follows because that pairing is a perfect pair.
Yeah. So you can pull out any.
Yeah. I mean, again, needs to check with this. I mean.
And that perfect pairing statement, I guess you can also make a combinatorial statement about de Maizière operators or something like. Is that something known in the representation ring? Like I guess in the language of Ben or something, it would be the fact that this is a Frobenius extension, that the fact that invariance inside the full representation ring is a Frobenius extension.
Fair enough. Yeah, I don't know.
Maybe a general question to what extent can one kind of categorify the ideas you've presented for the decategorified proof to obtain I mean, is this like proof strategy in general like still what one attempts on the categorified level by categorifying everything, or
I mean, let me say no. So yeah, it's not like the proof in Roman's paper isn't sent, right? Isn't proven by sort of generators and relation, like send BS to something and then check that all the, like it, yeah, it's just, right, proven by ideas, sort of, right. Let me explain one example, and then it's sort of combining a lot of ideas like this. But for example, if you have, right, an action of the representation category of G on a category, and then you have a tensor endomorphism of this action, meaning on any object tensor V, you have an endomorphism from this to you have an endomorphism from A tensor V to A tensor V, such that on the tensor product A tensor V tensor W, it satisfies some sort of derivation relation. Then you have an action of the category of the Lie algebra mod G on the original category. So some Tanakian formalism like this. And then using like a bunch of stuff like that, you sort of construct an action of basically this, of the Grothendieck, right, of the Grothendieck, of the category of coherent sheaves and of the Grothendieck-Springer, on, right, sort of on both sides, a left and right action. And then you sort of construct the map by acting on the left and on the right on a particular object, which sort of corresponds to this E minus, and this will give you the equivalence. I don't know if this is a very clear, yes, I don't know if explaining two realizations in 2 seconds was very successful, but yeah, let me just say that yeah, it follows along different paths that just like checking generators and relations. But the fact that there's a braid group action on this category, there's this work by Beshukavnikov and Risch, the braid group actions on the derived category of the Springer resolution or something like this. This does follow this idea. This is also by sort of, yeah, generators and relations like this. Yeah, I don't know if that answers the question.
Yeah, thanks.
Any other questions for Pablo? If not, let's thank him again. And so I just want to say we are going to spend quite a few of the next weeks talking about two realizations. So the outline that Pablo just gave in 2 minutes will expand to I don't know how many hours.
Probably more successfully.